Okay, fine. So then we start. Okay.
So, sir, I will be making you host, and you will let the student in once they will suppose any student left out to join. Suppose they will
Okay.
be joining after 10 minutes. So after that, like
Okay. Okay. So
yes, sir.
I will get one notification, right? That
Yes, sir, yes, sir.
somebody is okay. No issue.
Yes, sir.
Okay. 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 Then we start here. So now. Okay. So I am Manish Jaswal from IIT Jodhpur, and I'm working as what like freelance gate trainer for iitiansgateclasses. So I'll be teaching you thermodynamics. So for HAL part, right? So let us first understand that what we need to study in thermodynamics. So what will be the coverage of syllabus, right? Like how do we proceed and what are the things which we need to know before we appear to the exam. So first thing we'll be knowing here is that what is the basic concepts like which will be helping us to build our subject when we are moving to the application parts of thermodynamics, like you will be moving to the RAC or maybe power plant and all. So there you understand that okay, the thermodynamics is the basic thing like which gave you basic concept to analyze the thermal instruments like which we are using to convert thermal energy to change it into another forms, right? So the first thing is basic concepts. So here we will understand that what are the basic things which we should be aware before analyzing any thermodynamic equipments and all. Okay, and the second thing then we will move to is zeroth law, and then we move to first law of thermodynamics. So here what we do is that we'll understand what is first law of thermodynamics, and then we will apply it to certain certain equipments like we'll apply it to turbine, let us say any general equipment which is producing some power, right? And then we will move to what that that is second law of thermodynamics. And then after second law of thermodynamics, we'll move to that what are the learnings which comes out from second law of thermodynamics. Let us say entropy is the very important property which we learn from second law. So based on that, we will be knowing that this concept like available or unavailable energy. So availability, I am writing in short. So availability and other things we'll discuss, and then we will move to what properties of pure substances. Properties of pure substances. So this is how we will be proceeding. And see, for any PSU exam, what we should be focused upon that we should learn the concepts, and then we should apply these concepts to the problem solving also, because problem solving becomes very important part when you are appearing any exam, because concepts are same, but it is the question which makes the exams different, right? So every time we will be learning any subject, we should practice ample amount of questions so that we are aware of the kind of questions which we are going to face in the exam, so that we know that how to apply, like what should be your problem solving techniques while sitting in the exam hall. So it's very important that simultaneously we'll be solving what the problems based on this which are appearing in the PSU exams, or mostly we'll be covering those questions which have already been appeared in some standard exams like some PSU exams or any assistant engineer exam or ESE and GATE exam. So we'll be solving questions through them, and if we are through those questions, then the questions which we'll be facing sitting in the exam hall will be somewhere around these topics only. Or and moreover, we know that yes, we are already solved with ample amount of problems based on those. Then only thing will be that we will be sitting there and you will be recalling, because there in the PSU exams time is very limited, so we need to just recall things and we will answer those questions. Okay, so this will be my strategy, particularly in thermodynamics. Okay, so let us move quickly to the basic concepts part. So thermodynamics, anyway, the subject itself deliberates so many things. Thermal means what? That something heat, and dynamics is the movement of heat, and moreover the effects of heat, like what kind of forces are going to be produced with it, right? So thermodynamics in general, it means what? That this is the branch of science which deals with what? Which deals with energy interaction. Like every time we talk, anytime we talk about like any equipment, then we know that most of the time our mechanical engineer's role is to convert energy from some given form into some desired form, right? Like let us say we are having with heat energy, then we need to convert it into sometimes work, or sometimes we'll be having work energy, we need to convert it into heat. And this is what thermal background what thermal background engineers do particularly, right? So what thermodynamics will help you to know is that how to deal with energy and its interactions, right? So what is energy? Energy is something which has some ability to cause changes, right? So first thing we understood here is that what is thermodynamics. Okay, so this is the branch of science which deals with energy interaction and its effect on the surrounding. Okay, and second thing very important, that is energy. So what is energy? Energy is something which has some ability to cause changes, right? So if I possess some energy, then I have what? The ability to cause changes. Let us say that if I have some energy, then I can cause change. Like let us say that I can put my book from somewhere to somewhere else, right? So that means that I possess some energy, then only I can cause some change. So energy, what is it? That it is ability to cause changes. Okay, next. And then see, in any general thermodynamic problem, like let us say that you are analyzing a water bottle. Okay, like a water bottle is there which is left in your room. Then what you need to understand is that if this is the bottle, then your study is focused particularly upon this bottle and the surrounding which is in close vicinity to it, right? Like this cannot cause very what significant changes which is not in its close vicinity. Like a let us say that there is a water bottle uh, kept in your room, then it cannot cause very significant change into what? That the things which are very far away, or let us say that another let us say there is a chair, there is a book, or there is a fan in that room, then this bottle is not causing much changes to these other parts. That means what? That every time we need to focus upon what? Like let us say that if I am focused to study about that what are the things happening with this water bottle, then I precisely define that okay, I am focused about this bottle part only. So this bottle becomes what? This bottle becomes my system. Like I am trying to analyze this bottle that if there is some water heated into it, then what will happen after 5 minutes, 10 minutes, or 20 minutes, or how much heat it will give to the surrounding. Like, let us say, for now, this is your room. So, if there is a water bottle left in this room, if this is that room, then then your system is what, that this water bottle and anything other than system becomes automatically what, these are surrounding only. Got the idea? System and surrounding. Like any time which you, like whenever you are going to analyze any particular system in the nature, then what you are trying to fix is that where your study is focused, you create some boundary so that you can analyze your things on that region particularly, so that automatically becomes what, system. And the second thing is surrounding, like the close vicinity to it, like anything which is in close vicinity only becomes surrounding. Okay. And the third thing which we can see is that there is one thing called system and another thing called surrounding. So there is one which what, which creates a difference between these two, that is called what, boundary. So next thing is boundary. So boundary is what? It is the fixed or imaginary surface where our study is focused. Like I am focusing all my study into which boundary? Like this is that boundary. This is, see, this bottle is system, but the outer surface of it is creating what? Kind of boundary. Okay. So boundary is deciding, helping you to decide that what is that region. So here this boundary has defined that this is your region where you are focused to study that what are the changes happening in this region, right? So this is what called system, and this red part now is what, boundary. So boundary is nothing but what, where it gives you the surface where your study is focused. So it is the surface where our study is focused. See now, what happens with this boundary? See, boundary can be, sometimes we can see questions from this area also, that boundary can be, it can be fixed, it can be fixed, it can be imaginary, and it can also be what, movable. Let us see the example of all of these. Fixed boundary means what, that let us say you are analyzing uh, a nozzle. Then what we can see here is that there is something coming. Let us say that there was some fluid flow. So fluid is entering into this region and moving through this region at the outlet. So this becomes your outlet and this is your inlet region. So can we see that whatever happens with the fluid in this region particularly, I am focused about that what happens in this region particularly. Okay, so this becomes what, this is your system, that whatever will happen into this region you will study that only, that you are not worried that what happens beyond this region and what happens beyond this region, right? That maybe that fluid has some temperature, velocity, flow, enthalpy, entropy, and so many things. You are not worried that how system has attained these many things. You are only worried that once it has entered your system, which is now a nozzle, then you will be only worried about that what happens with that fluid flow in this region only, this green region only, and when it goes outside, then your study is limited to this area only, and when it goes outside, you are not worried what happens after that. Okay, so that is why we have defined system. Other way, if you have not defined the system, then if somebody will tell you, somebody will ask you that, okay, tell me there is a fluid flow in this nozzle, then they will ask you that, okay, analyze it thermodynamically. Then you will be confused that where you should take a start, that what should be your start point to analyze that problem, and where you should stop. So that is why you have created a system that, okay, now my study is focused in this particular area only. So I'm not worried about that what happens before this point and what happens beyond this point, right? So that is what system is. And what about boundary? See, can we see that these part of the nozzle, like let me darken it, these part of the nozzle are fixed, right? So this is anyway called fixed boundary. Okay. and and imaginary we can also visualize here. Can we see that I initially there was no boundary here? Why? Because there was only nozzle, so I can see only these two boundary. And what about the what the boundaries in lateral region? So those are termed as imaginary because these boundaries were not initially there, but you have created them what just for the analysis. So this is what called imaginary boundary. Okay? And these are the real ones and the fixed also. These are the real ones and fixed also. Okay? And this is imaginary, but this is also fixed. This is also fixed. Then what is movable boundary? See, let us say you are analyzing some problem in piston cylinder assembly. Okay. Then let us say that this piston cylinder assembly is at some given pressure and temperature, and then you give it some amount of heat. Then now again your study should be focused upon some limited point. Why? Because you are not worried that what happens to this piston. Why? Because your study is focused only upon what? Gas. Like whatever the amount of gas is inside it, I am focused upon that particular gas only. So you are not worried that what happens to this piston, what happens to the cylinder walls also. So your study is now limited to whom? Only these gas. So you create again a boundary, and anyway this is the real boundary. So you create a system here, and this becomes what? Your system. So here what we can see is that once the gas is heated, this system boundary, or anyway this piston can move. This piston can go upwards. Then what will happen? This gas will occupy another position. Let us say that if this piston has moved to this position, then this gas if I imagine that there is no piston at this point, then what will happen? That this given gas which was at this point only, now it will occupy this space also. So now can you see that earlier your system boundary was this one, but now your system boundary is this one. So can we see that this boundary is nothing but movable? Okay, so I hope all of us are through with what is this is imaginary boundary, the real ones, the fixed ones, and the movable ones. Okay, next. So let us now understand what are the types of system. Very important. So every time we can expect one questions, like one easy question can be appearing from this area. So types of system, depending upon the fluid flow or depending upon the nature of your device, we divide system into three parts. One is called open system. So what does it mean, open system? And there is one thing called closed system. We'll understand it one by one. Comparative study always helps us to understand things better. See, what happens in the open system and closed system is as follows. In open system, see, once you have defined any system, then let us go to the previous slide. Can you see that here regularly some fluid comes in and some fluid is regularly going out? So can we see that there is some interaction, and which is in the form of what? Mass. Can we see that? So there is mass interaction, and here if there is no ball, and which I have already drawn that there is no ball, then can you see that whatever the mass was inside it, the mass is again fixed. Why? Because the mass is not allowed to move outside the system. So here your mass was fixed. Mass is fixed, right? And here your mass is not fixed. Mass is not fixed. Means mass interaction is allowed. Means mass can come in, mass can go outside. But in this case particularly, what I could see is that mass is not allowed to leave the system. Can we see that? Anyway the boundary is moving. That means mass is fixed, but volume can change. Can we see in this example? All of us should appreciate this fact that yes, this boundary has moved. That means this volume has got changed, but the mass is same. So mass is fixed and volume is changed. But here can we see that mass is not fixed. Any lesser mass or higher mass can occupy depending upon their density, right? Why? Because we know that mass is nothing but density into volume, right? So depending upon this density, this mass can get varied. So these are the problems where we are studying compressible flow, like when density mass also in particular region can get changed. Okay, so here mass coming in is not fixed. Okay, but can we see that once you have defined your system, then this volume is fixed anyway. Like this packet is always fixed, this is not going to change, right? Like this volume is always fixed. So can we see here that mass is not fixed but volume is fixed, right? So we have created the basis anyway for need to classify the system. Why? Because I can see that somewhere there is interaction of mass and the volume is fixed, but I can see somewhere else that mass was fixed but volume was getting changed. So this is the need to classify your systems into two parts. One is called open system and second one is closed system, and the third one is isolated, which we will study next. So what happens in the open system, that we have just now seen that in open system mass interaction is there. Mass interaction is there. We have seen just now that there was one system. So we name that system, this system where mass interaction we can see is the open system. So mass interaction is there, but volume we saw is volume is fixed. And what about energy interaction? Anyway, you will have to allow energy interaction. Otherwise, what will happen? There will be no need of then such devices now. If you don't allow energy interaction, then how your system will change its state and other things. So energy interaction is always there. So energy interaction is allowed. So these three things about open system you should know, that energy interaction is allowed, mass interaction is also allowed, and volume is what? fixed. And what are the examples of open system? Nozzle, just now we have seen nozzles, or most of your devices like boilers, steam turbines, all of them are what? Compressors. All of these are what? Open system. Means here you're continuously some mass comes in, you give some energy to it and mass goes out. But the reason in which mass enters, like which is called volume, we have seen here that this like why? Because it's not changing, so volume will remain fixed. Okay, and let us come to closed system. So in the closed system, what will happen? There will be energy interaction, we have seen already. So there will be energy interaction, and then there will be mass interaction. No, mass interaction is not allowed now. So mass interaction is not allowed. Okay, and what are the examples? We have just now seen now that piston cylinder arrangement without what? Valves. So piston cylinder arrangement without valves. Next. And the third thing is isolated system. Isolated system. In the isolated system, there will be no interaction of mass, no interaction of mass, and there will be no interaction of energy as well. No interaction of energy as well. Like what are the example? Like well insulated thermoflask. What happens that there is a well insulated thermoflask, like this is, let us say, insulated. Okay, then what happens that once you pour some water into it and you cover and you just what cover this one from upside also, then what happens that let us say there was some water into it, then this water is not coming, if this water is not allowed to go outside, and if it is well insulated, so there is no energy interaction, like there is no energy interaction, then this is an example of what? Isolated system. Energy interaction is not allowed, and mass interaction also not. And the best example of it is universe. Okay, let us move to the next. So once we know these system, then while analyzing, what things we are focused upon, like when you are analyzing any change in the system, then you are particularly focused upon what? Changes in property. So let us understand that what are properties of the system. So like let us say that you are analyzing a flow through nozzle, let us say you are analyzing flow through a boiler, let us analyze that you are compressing some air, then you will be analyzing it, right? Like you will define some system and then you will start analyzing it. Then while analyzing, your focus will be what? That let us try to find out what are the changes in its property, and those properties change will help you know that what changes has occurred into this particular substance which was going through that system. Okay, So can I say that any characteristic of the system is called property? Okay, next. Then properties are, these are those characteristic which which will uh, help you know that what are those properties, like what can be the characteristic. Like you can be characteristic can be what, like I have some pressure, I have certain kind of heat with me, I have certain kind of energy with me. So these are my characteristics, right? And then I specify them in terms of what, properties. So my characteristics are nothing but what, properties, right? So these properties are then classified into what, two things. And one is the classification. If I talk about classification of property, then first thing is intensive property. And again, we'll study it comparatively. Second one is extensive property. See, I hope you understand what is meant by property. Like, let us say that I have some heat. So this is characterized by whom? Temperature, right? Let us say that I have some ability to put some pressure upon it. So how it is characterized by that particular value of pressure. Let us say that I have some energy, then characterized by whom? Internal energy, enthalpy. So these are the things which is called what? Properties. Okay, then these are defined like intensive or extensive based upon that if they are mass dependent or independent of the mass. So what is intensive property? Intensive properties are those property which are independent of the mass. These properties are independent of the mass. Independent of the mass, whose mass? Of the system into consideration. And what about extensive property? Here your properties will be dependent upon the mass. So this is extensive property. These are dependent upon the mass of the system. Mass of the system into what consideration? Okay. So let us understand that which properties are independent of the mass. Let us say that how we can understand it very in precise manner or in very general form. Like uh, how do we understand it? Let us say that mm, we have a chamber in which some gas is filled. Okay, let us say there is some gas. So you will automatically understand what I am trying to deliver here. See, so this gas filled into a chamber, it can have some which property? It can have pressure, it can have density, it can have temperature, it can have some energy. Let us say U. U is denoted like energy and it can have some entropy also. Okay, so all these terms are absolute, not specific. Like all these terms are specific, absolute. Specific means what? Per unit mass. So what you will do in order to identify that if the given property is intensive or extensive, we will simply divide this system into two parts, and then we will pick up that property and we'll see that by dividing can we see any kind of change into that. So let us first move to pressure. That can, if when you half the system, like when you have divided system into two equal parts, then can you feel that the pressure will anyway remain same? Why? Because pressure at any point in this system will remain same. So even though you pick a small amount of mass from this point, then pressure of that particular mass will be again same only. So that means pressure becomes intensive property. Okay, so I am helping you know first what are intensive property. If it will be extensive property, I will write those property here. So can I write that intensive property example of this one is pressure? Okay, let us talk about density. Density is nothing but per unit mass, volume per unit mass. So can you see that if you are picking some gas from this point or any point, or if you have divided into two equal parts, the density is not going to change. Density will always remain same. So density is again what? Intensive property. So I'm writing down here. And what about temperature? Temperature will again remain same now. Why? Because it is uniform temperature of that particular gas. Like everywhere, wherever you go, you will find that temperature at this point, or anywhere. Like if you pick something from here, the temperature will again remain same. So the temperature is not being changed by dividing into two equal parts. Let us say, for example, you have a piece of bread, okay, and if you cut it into two equal parts, you will never feel that by cutting into two equal parts, the temperature of this one and this one has got changed. No, the temperature will always remain same. So that means temperature again becomes what? Intensive property. And likewise, you can analyze density also. Like let us say that you have taken some let us say that my example of bread again. Let us say that this is made of wheat. Okay, so wheat has some particular density with it. So if you cut it equal parts, this will never happen that the density will get changed, like density will get half. No, never. Density will never get half. Density will always remain same. So all these things are what? Independent of mass, so becomes intensive property. Now let us talk about internal energy. Now energy is very much dependent upon what? Mass. Why? Because this system as a whole was constituting this much of mass, this much of energy, sorry, this much of energy. But now since you have divided this one, then this part will consider half of the energy and this part will consider half of the energy. That means your energy is nothing but extensive property. And see, I am writing it in capital letters. Capital letters are for absolute, and if I write it with small letter, that means it is the meaning of U per unit mass. Okay, we'll talk about this one also. So let us first finish this one. And what about volume? Again, if you divide it into two equal parts, volume is also getting changed. That means this is dependent upon this one. And what about entropy? Again, this will be why? Because if I talk about that S was the entropy of this whole mass. Now, if I have divided into two equal parts, then again this will be S by 2 and S by 2 if it is in two equal parts. So can I say that this is also nothing but extensive property? Okay. Now, I told you repeatedly one thing, specific terms. Specific. Specific means what? Given property upon given property is divided by whom? Mass. So property per unit mass is nothing but called a specific property. So for example, let us say here we were talking about U, V and S. Now instead of capital U, if I have written small u, that means specific internal energy, then I have already made it independent of mass. Why? Because I have converted it into what? Let us say that if this unit was kilojoule, then it has already got converted into kilojoule per kg. then again if you divide it into two equal parts, this part will be having same specific internal energy compared to this one. That means specific internal energy or any specific property when is not getting changed when you divide system into two equal parts. So can I write down one thing as a note, that specific properties are intensive property? Can I write down that specific properties all specific properties are intrinsic properties? I hope till this point all of us are okay. Okay. Now let us talk few things about properties. Properties are very important. Properties are point function. Properties are point function. What does it mean when I say point function? Let us understand quickly. Okay. See, when I say properties are point function, let us say that there was one container and it was having some water in it, okay, and then you applied some heat to it and it has got let us say initial temperature was T1 and then T1 has got changed to T2 when you applied some heat, okay, and let us say that instead of applying directly heat you applied some water heater into it, okay, and then again it was have same system, means this one is identical to this one, means the water is again the quantity is same, then again initial temperature was T1 and then final temperature is T2. So see how you have reached from T1 to T2, this property is never minds, okay, means this T2 your goal is to reach T2, how it has reached T2 you don't mind, okay. So that means properties are defined at a point only, means you if this was T1 then you have reached to T2, and how you have reached T2, this is not the concern of properties, this we will take care somewhere else, but properties are only what point function, that your goal was to reach T2 you have reached T2, your goal was to reach T2 you have anyway reached, right? So you don't mind how what the path it has taken or what process you use to reach from T1 to T2, it never minds, it will never happen that if you are willing to reach T2 then it will never happen that you cannot reach it through any other mean, right? So it simply means that you are only dependent, you are only interested into what is your final temperature, okay, you are not worried that what happens in between. So that is why very important properties are point function. So if it is not dependent upon that what path it has taken, then can I say that properties are independent of the path, or we can say that independent of the past history? So we can say that properties are independent of past history, okay, and then it has exact differential. Why? Because if it is not dependent upon path history, so what I can write down that it is exact differential. What does it mean? That if I have reached from T1 to T2, then dt can directly be written that this is T2 minus T1. It never minds that what is that process it has gone through. Okay. Okay. Now let us try to understand one very important. See, till now we have understood that there is some system, we need to analyze it, and then we knew that how we define the system, and then we then we understand is that we analyze the system with the help of what properties, and then you need to you know how you are going to analyze your system. Why? Because when system is changing its states from one state to the another state, then it is continuously changing its state, right? Like state nothing means it. It means that, let us say that you were at some temperature T1 P1, okay, and you had some water, so it has some temperature T1 and P1. So this is one particular state. Let us say that from T1 P1 you have reached to T2 P2, okay. Then this is another state, okay. So you have reached from this point to this point, okay. So this is the property, T1 has got changed to T2 and the pressure has got changed from P1 to P2. So the properties are point function, then you only worried about that what is T1 and T2, but what path you are following reaching from T1 to T2 will define that how much energy you need to get interacted, right? Like this will help you know, this helps you know, this path helps us to know the amount of energy interaction. Okay, so anyway the amount will be same. Again, how you have reached it now, this you need to analyze every time, okay. So then it can change its states from T1 to T2. So how do we analyze? Like this is never like that from T1 to T2 will happen in a moment. There will be some time included into it, right? Some time will be passed, then only this T1 will reach to T2. That means between this T1 to T2 there will be infinite number of states. Like if T1 is one individual state and T2 is another particular state, then between T1 to T2 there must be infinite number of what states through which this has gone. So that change from state 1 to state 2, that change from state 1 to state 2 through which it has gone is nothing but process. You must have heard those things, but let me help you know that what is the physical interpretation of it. Like T1 is one state, so this is state 1 and this is 2 and this is state 2. So from state 1 to state 2 you have reached through whom? Through process, and between this process 1 to 2 we have infinite number of what particular states. Then we need to specify, we need to understand this process, like this can happen anyway. So this process will help you know that how much energy you need to put into the system, okay. So how we analyze this is one thing is called, how do we analyze it, is quasi static process. So let us understand what is quasi. See, if see, if all the changes from 1 to 2, like we can see now that all the changes from 1 to 2, if it will happen automatically, means within a second or within a fraction of a second or within no time, then you will not be able to analyze how this has gone through the changes. You need to find that path through which it has gone, then only you will be able to find out the changes in that particular path, right? So quasi-static process helps you to know that what I mean by quasi-static means quasi almost like almost, and static means what? Static, we know is static. What does it mean? Okay, so quasi static means what? That you are almost in equilibrium condition every time during this process. So what does it mean physically? Like if I was at T1 and I was approaching T2, then from T1 to T2 there must be some change. So that change, let us say for one instant, let us say that if you were at T1, then at next process you are T1 at T1 plus 0.001 degree Celsius. So can you see that this is in equilibrium only, like there is no much change in this state, like you have started your travel from T1 to T2, but you are walking through what? Infinite number of states. So your next state is nothing but T1 and T1 plus 0.001 degree Celsius. So can you see that there is very less difference between these two? So can I say that this is nothing but in equilibrium state only, that if it has happened through very slow process. So quasi static means what? Very slow process. So can I see that if the process is quasi static, then I can say that it has passed through n number of equilibrium states only. Okay, so how can I say that a process is quasi static? If it takes place infinitely slowly. Okay, next. Now, so if let us say that we are trying to plot our temperature change. Okay, let us say that for example you are trying to find out that you are reaching from T1 to T2. Okay, then then this is that path, right? So if you know this equilibrium state, this equilibrium state, this equilibrium state, this one and number of this equilibrium state, then only you will join them, and then you will say that okay, this path is defined, this path is defined. Okay, so path is only defined when your process has taken quasi statically, otherwise you don't know that what is your next equilibrium state. Okay, let us say that if I was at this point, then I have idea of this point. Let us say if this is T1 and this is T2, similarly if this T1 and this is T2, then you have only idea about that what happens at T1 and what happens at T2, and you don't know that when it has gone through the several number of states, then what was the next state, because you have not gone through equilibrium states now, then you will be not able to identify that what will be your next state and so on. So you draw it what? Through series of dots, and but here we can draw it through a solid line. So I hope we understand the difference between quasi static and non quasi static process. Okay, and then we move to, this is non quasi static, this is quasi static, and this is non quasi static. Then let us understand reversible and irreversible process. See what is this? Then these are the tools which will help you to analyze your system later on. Like if you know these tools, like what is property, what is quasi static process, what are reversible and irreversible process, what is property, how to define system, then these tools are used in any part of what thermal background. Let us say that in refrigeration part, in IC engine part, in power plant, everywhere we are using the basics of thermodynamics. Okay. So next thing is reversible. So reversible and irreversible process. Reversible means what? That if you, let us say that you have started your journey from T1 and you have reached T2. Okay. And then when you reverse back from T2 to T1, okay, you have gone from T1 to T2, and when you reverse back, then when you reverse back now, if there is no effect left on the system, why? Because always whenever we are analyzing any system, we define our system and surrounding. So when you are traveling back, like when you are reversing your path, and if there is no net effect on the surrounding, if there is no net effect on the surrounding, on the surrounding surrounding when you have followed the reverse path, when the process is reversed, then we call it what? Reversible process. And what is irreversible process? Anyway, different what opposite of this one, that when you take the reverse path, like reaching from T1 to T2, and when you are coming back, then it is not possible that without taking something from surrounding you will reach to this one. Then that process becomes automatically what? Irreversible. Okay. So why we have studied quasi-static? See, quasi-static process are the basic requirement for a process to be reversible. Okay. So quasi-static processes are reversible in nature. Okay. And irreversible process, a non-quasi-static, the main reason for talk about it later, and the main reason is friction and non-equilibrium. If you are able to maintain the equilibrium condition, see what does it mean equilibrium and non-equilibrium? Suppose you were at 10 degrees Celsius and you have reached to 10.01. So what it will make you feel like that 10 and 10.01 are identical. So then there will be no drastic change into that particular system. If there is very drastic change, then there are losses bound to happen. If the changes are not drastic, then I can what? Stay in equilibrium condition for rest of the time. Okay. Now, let us understand how substance, like we have understood the system, right? So then there is one thing called pure substance, or when you are studying any system, then you specify that kind of substance you are dealing with. So the thing is pure substance. Pure substance. So what is pure substance? If substance is called pure substance, if it has pure substances has uniform, or homogeneous is more general word, has homogeneous chemical composition, homogeneous chemical composition throughout, chemical composition throughout. See, what does it mean when I say that has homogeneous chemical composition? See, your study will be limited to pure substances only. Why? Let us see. See, what does it mean pure substance? let us say that there is a container into which there is some water and there is some, let us say, vapor. So there is some water settled on the downside and there is some vapor in this part. Okay. And these two are in equilibrium. This is vapor and there is some water into it. So I am focused upon whom? Chemical composition. Mind this word, chemical composition. Okay. So how do you check that if this is the pure substance or not? What you will do, that you will pick some amount of substance and you will try to identify what is the chemical composition. So what will be the chemical composition here? Nothing but the 100% of H2O only, like water, the chemical formula. And what about if you pick some amount from the vapor side? Then again you will find out that there is 100% of H2O only, no other substance. Then can you say that although there are two phases, like there is one water and like liquid phase and vapor phase, but this is pure substance. Why? Because it has got what? Homogeneous chemical composition. Like wherever you wish, you pick some amount of that particular what substance, and then you try to identify that what is the chemical composition. Wherever you will pick, you will find out that this is nothing but 100% of H2O. Okay, so this is called pure substance. Okay, and let us say that you are analyzing any gas. Okay, in gas form only, there is no liquid gas. Then can you see that if there is some gas into it, there is some gas into it, then if you will pick up some amount of gas, let us say that in this particular system I have fixed my system to like some air. Okay, there is some air into it. You pick anywhere, from anywhere you pick some gas. Okay, then you try to identify its chemical composition. So you will find out that it has chemical composition highest nitrogen, oxygen, and in the decreasing order of other gases. Similarly, nitrogen, oxygen, hydrogen, and all. So you will find out that what chemical composition you found at this point. You will find out that the same chemical composition is followed you throughout the system. Then we name it as that this is nothing but chemical composition throughout. Name it as pure substance. Okay. Then what are the examples where we can see that there is no pure substance? Let us see. See, let us see when we are picking a container in which there is some oil and water put into it. So what oil is anyway having lesser density, so oil will get settled on the upper part of this container, right? So this is oil and water mixture. So now if you try to check the chemical composition at different word positions, then can you see that there is 100% of water here, and if I take some amount from this one, then I would identify that this is 100% of H2O. So, sorry, oil. So can I say that this is not pure substance? Why? Because somewhere I have 100% of water and somewhere I have 100% of oil. That means this is not homogeneous composition. Homogeneous means what? That if I am getting same composition throughout that particular system, but here we can see that it has not followed that way. So this is not the pure substance. Okay. One question which keeps coming on in the exam is that the mixture of liquid and gaseous air, if it is the mixture of liquid substance liquid, gas, and gas if it is pure substance. Let us say there is some liquid air, like air can get condensed now at their own particular temperature, pressure, they can get what condensed. So there is some liquid air and there is some gaseous air. Okay, so again, this uh, this is not pure substance. So how do we identify it? This is the mixture of, this is the mixture of what? This is the mixture of gaseous air plus liquid air. Gaseous air plus liquid air. So what I can see, that there will be some liquid which will be settled at the bottom of the container, and there will be some gaseous substance at the top of the container. So one thing we need to appreciate, that air is mixture of n number of gases. Let us say that oxygen, nitrogen, hydrogen, and etc. Then can we see one thing, or we will later know that this oxygen have their own condensation pressure and temperature. Similarly, nitrogen have their own condensation pressure and temperature. Similarly, hydrogen and other substances. Then what will happen, that your system will have one unique pressure and temperature. This cannot assume n number of pressure and temperature at one instant. That means that if it is having one instant of pressure and temperature, that means it can have, it will only condense those gases who satisfy, whose condensation pressure and temperature you were able to achieve. That means, let us say that if this is the mixture of let us say hydrogen, nitrogen, oxygen, then what you will feel, that there will be a layer, and that to these layers, these liquids, gases will not mix with each other. So what I will appreciate, that there will be layers of, let us say that there will be one layer of oxygen, there will be one layer of nitrogen, and then there will be one what layer, or let us say that gaseous substances who will be having in let us say oxygen and nitrogen has got condensed, then there can be hydrogen and other gases. So can we appreciate this fact, that this is not again pure substance? Why? Because I cannot find homogeneous from another, so I can say that no, this is not an pure substance. Okay. Okay, let us move to the next. Then there is one very important rule called Gibbs phase rule. See, why we need to understand this one, Gibbs phase. See, we have seen that we are having n number of P's, right? Like temperature, pressure, density, volume, enthalpy, entropy, and other things. So whenever you are analyzing any particular system, then you will have to identify all these properties, then only you will fix that state. Yes or no? Like I told you, what is state? Like state is fixed by what? A set of properties. So if you are trying to fix one state, then you will be need to identify what is pressure, what is temperature, what is density, what is internal energy, what is enthalpy, what is entropy, and lot many things. Okay, so can we see that this count is anyway going to be increased in more number of, when you are applying it to complicated systems, so this number will keep on increasing. So this Gibbs phase rule came into picture. This help you to know that what is the minimum number of, it helped you what, to identify the minimum number of, it helps you to identify, it is not Gibbs phase rule, it helps us to identify identify minimum number of minimum number of independent 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 intensive properties intensive properties intensive properties required to fix the state of the system, to fix the state of the system. So what is Gibbs phase rule? Gibbs phase rule connects with you with what? Number of phases plus degrees of freedom. This is nothing but degrees of freedom. Okay, and this is equal to C plus 2. So here P is number of phases, F is degrees of freedom, C is number of components, okay. So can we see that Gibbs phase rule helps you to identify that what is the degrees of freedom of any given state, and when you know what is the degrees of freedom, then you will be able to identify that how many minimum number of independent intensive property you need to specify so that your state is completely what, defined. That means this which I have told you here is nothing but this is degrees of freedom. So what is degrees of freedom? This is nothing but that this minimum number of properties you need to tell me so that I will fix these two, then rest of the others will automatically follow. Getting the idea? That let us say that degrees of freedom is 1. That means that I need at least between these property at least one which is independent, and I need to identify, for example, temperature. At my specify pressure, then other things, let us say pressure, density, and all other properties will automatically follow. Then your system will be what, completely specified. Okay. Why? Because whenever you are analyzing your system, then you need to specify it now, that what are the property, temperature, what are the density, and other values. Okay. So degrees of freedom helps you to identify minimum number of those. Listen this word, minimum number of what, independent intensive property. Mind the word intensive property. Okay. So let us try to find out degrees of freedom for some given states. For example, let us say that I am having water and water vapor with me. Okay. Then tell me what will be the degrees of freedom. So let us count number of phases. There is one water and vapor. So number of phases here is 2. And what is the components? Components is anyway 1 only. Then how do I identify the degrees of freedom? So degrees of freedom will be nothing but I am putting this value into this equation. So P is 2 plus F is equal to C is 1 here, 1 plus 2. So can I see here degrees of freedom is 1. That means if I am having water plus water vapor, then if I identify one property only, then rest all of the other properties will what, automatically follow. Got the idea? So I need to identify only one independent intensive. Mind this word, I am telling you again and again, independent intensive property. Okay, so I will be finding one independent intensive property and I will be automatically finding out the rest ones. Let us say we are applying this concept on triple point of water. Triple point of water. Okay, then what happens at triple point of water? We have number of phases which is existing in equilibrium, coexisting in equilibrium is 3. Okay, means here solid, liquid and gas, all three phases are coexisting. Okay, and components is anyway one only, that is water. Then when you apply this Gibbs phase rule into this one, Gibbs phase rule is what? P plus F is equal to C plus 2. Then here your P is 3 plus F, C is 1 and plus 2. So here your degrees of freedom, triple point of water, your degrees of freedom is what? 0. That means that whenever your degrees of freedom is 0, it means that your state is fixed. That means triple point of water is what? A fixed point. Whenever I got a degrees of freedom as 0, that means this is fixed point. What does it mean? This is fixed point. Okay. Okay. Moving to the next. Then when you are done with this one, like till now, what do you know? That what is system, what are the state, what are paths, process, surrounding, what are the properties, how to find the changes, what minimum number of properties you need to identify. These many things now you know. Then you know that your system should coexist in equilibrium every time. Then only you are able to what? Means apply your thermodynamic laws, and you can study it in more precise manner. So in order to understand the system, you should be always into what? Thermodynamic equilibrium. So you should be lying everywhere what? In the thermodynamic equilibrium. So what are the conditions which we need to follow, or which needs to be followed by any system? Then it will be under the thermodynamic equilibrium. The very first thing is that you should be in thermal equilibrium. Thermal equilibrium. What does it mean? Thermal equilibrium means what? That there is no scope left for heat transfer. That is why, see, I told you now that in order to stay in equilibrium, your temperature changes should be very low. Let us say that if you were at 10 degrees Celsius, your next state is 10.001, next state is 10.002, next state is like that 0.003 and all. So what does it mean? That if the temperature change is very low, then there will be no scope of heat transfer. Then only you will be satisfying one of the condition for thermodynamic equilibrium, which is called what? Thermal equilibrium. So here there should be no scope left for the, no scope should be left for heat transfer. Okay, one thing. Second thing is mechanical equilibrium. Mechanical equilibrium. See, what happens in mechanical equilibrium? Like thermal equilibrium, we see that there should be no scope of left for the heat transfer. Here, there should be no scope for what? There should be no tendency of any movement into the system. That means that your forces should be perfectly what? Balanced. So the forces should be balanced. Here, forces should be balanced. Okay. And then the third one is chemical equilibrium. Very important, chemical equilibrium. What does it mean, chemical equilibrium? See, let us say you were analyzing certain gas. Then this gas has got its chemical composition. Let us say it was expanding or it was being compressed. And when there will be the tendency of chemical reaction within the system, then what can happen? That it can generate some force, or it can change the temperature even. That means that both of these equilibrium will automatically get what? Violated. That means the chemical equilibrium should be simultaneously maintained in order to achieve what? Thermodynamic equilibrium. Because if your chemical equilibrium is not maintained, then what happens that there can be chemical reaction occurring into that particular system, and the results of these chemical reactions, let us say that there can be some force, there can be temperature change, there can be, let us say that very high volumetric change, there can be very high volumetric compression, any change, then your system boundaries and other thing will start moving, then it will not be maintained in the equilibrium. So whenever you are trying to achieve chemical equilibrium, what do you mean? That their chemical composition should not change with respect to what type? Can I write that chemical composition should not change with respect to what time? Clear? So now we know that whenever we are trying to analyze this system, we are analyzing those systems which are in thermodynamic equilibrium, and what are the scopes of what are the conditions which we need to satisfy. One is thermal equilibrium, second is mechanical, and third one is chemical equilibrium. If all these three equilibrium conditions are maintained, then only we are in what? Thermodynamic equilibrium. Simple. Okay. Now till this point we are done with all the basic tools which will help us to analyze any thermodynamic system. Then let us quickly move to Zeroth law of thermodynamics. Like basic tools, whatever were needed, we are done. So let us move to very important discussion, that is Zeroth law of thermodynamics. See, one thing is that why zeroth, then first, second, why not first, second, and third? Very simple is that earlier first and second law of thermodynamics we were having, and later on this zeroth law of thermodynamics came. This law is associated with the what? Temperature measurement. This law is associated with what? Temperature measurement. So in short, we can write down that this law is the basis for what? This gave you basis for temperature measurement. Then can you believe that the basic tool in your thermodynamics is what? Temperature. Why? Because most of the time we are talking about heat. And when we are talking about heat, it is what? like temperature is quantified by heat. You can understand in this manner also. Like let us say that I am having ample amount of heat, then this is the temperature which quantifies me. Okay, so temperature is the very basic tool in order to analyze thermodynamic systems. And earlier first and second law came, which were not talking about temperature measurement. Then this zeroth law came later. So that is why we named it zeroth law, not third and fourth. Why? Because zeroth law, it should have appeared before first and second. Why? Because this is the basis for temperature measurement, and temperature is the very basic tool for what? For your analysis of any thermodynamic system. Okay, so that is why this is named as zero. So this law says that if there is a body, A, okay, this body A is in thermal equilibrium of another body C. Getting my point? There is a body which is in thermal equilibrium with body C. Then there is a body which is another body which is also in thermal equilibrium with C. Got the idea? That if I say that thermal equilibrium, that means I can necessarily say that this must have been satisfied. Yes. Another body B which is in thermal equilibrium with C, then zeroth law told you that then necessarily this TA must be equal to TB. This is very amazing fact, that why this law was even needed, that you knew from the mathematics that if A is equal to C, B is equal to C, then A is automatically B. Then why this law was needed, that you are teaching it me, that I can automatically say from my senses that this is what this one. But this law was very much needed. Why? Because I will help you through one example. Let us say that there is a room. Okay, there is a room, and in this room there is a metallic chair, and I'm just writing down with the help of, there is a metal seat, and there is one wooden seat. Okay, wood. And let us say that there was an AC functioning into this air condition was conditioner was functioning into this room, and this room has attained some uniform temperature of, let us say, 21 degrees Celsius. Then when you entered into the room, and when you will touch the metallic seat, then you touch the wooden seat. Once you touch the metallic and another time you touch the wooden seat, then what you feel, that your senses tell you that metallic one is the colder one, and the one which is made of wood is having bit higher temperature compared to metal. But this is mystic, right? Like this is demystifying. Why? Because your zeroth law says that if there is a body which is in thermal equilibrium, here this is your room, which is that body C, then you said your zeroth law says that if there is a body A which is in thermal equilibrium with body C, and there is a body B, this is body B, and it is in thermal equilibrium with body C, again that room, then its zeroth law tells you that this must be equal to this one, and this is true also. That means my senses here were what? Misleading. My sense to judge the temperature was misleading. That is why this what? This zeroth law was necessary, because if we were what, checking temperatures by our senses, then our senses were wrong here, and absolutely wrong. Why? Because if this whole room is at 21 degrees Celsius, and I told you that it has attained its uniform temperature throughout the room, then it must happen that that metal and wood, both of them are at same temperature. Then how can it happen that my senses are telling that metallic one is colder one and the one which is made with wood is having higher temperature? The only thing is that my senses are not working here properly. Okay. Then there was the need to develop what? A thermometer which will help you to measure what? Temperature. So zeroth law, here what we saw, this body C, this room is one which is helping you to know that if this room is at 21 degrees Celsius, then automatically wood and the metal is at 21 degrees Celsius. Getting my idea that if this room was at 21 degrees Celsius, then this wood plank and this metallic sheet, both of them will be at same temperature. That means the body C in the zeroth law, the body C acts as what? Acts as thermometer. This body C acts as nothing but thermometer. So your thermometers are based upon what? That C, like your body C is thermometer. Then whenever you are trying to find out some temperature, then you need to find out the some change in thermometric property. Why? Because you should know the variation of your property with respect to temperature. And let us say that uh, let me help you through the examples directly. So thermometers are based upon what? Finding out thermometric property. Thermometric property. Okay. So what are those thermometric properties? Let us try to identify. So based on finding out this thermometric property, we have a number of thermometers, and let us understand them one by one. One is resistance thermometer. Resistance thermometer. What is this resistance thermometer? See, see, we have heard the name Wheatstone breeze, right? Wheatstone breeze. So resistance thermometer works upon what? Wheatstone breeze principle. And here your thermometric property is change in resistance. So thermometric property is change in resistance. So can I write down this is nothing but delta R? See what happens in Wheatstone base. Let us say that you are you were working at some temperature. Now your temperature has suddenly changed. Then if there is some change in delta R, and if you know the relation between R and what? Temperature, if you know this R as function of temperature, then you can find out delta R by Wheatstone breeze, and then you will find out that what is delta T, right? So if you know what is the delta R, then you can know that what is delta T. That means your thermometric property here is change in resistance. That means that with the help of change in resistance, you will find out what is the change in temperature. Okay. So this is working as what? Nothing but thermometer. Second one is thermocouples. Thermocouples. Thermocouples based on works upon which principle? This is called Seebeck effect. Seebeck effect. What this Seebeck effect says you is that if there is two different metals, okay, and they are joined together at different junctions at different temperature, then there will be an EMF produced, and this EMF again produced is directly proportional to the temperature, that is delta T. See, what I'm trying to say is that, let us say that there are two different metals wire, okay, one is meeting here and they are meeting at some other point, let us say this one, and there is another which is meeting at here, one point here, let us say this is A and B. If there is one temperature, let us say this is TA and this is TB, and if there is difference between TA and TB, then there will be an EMF automatically introduced between these two, okay, and with the measurement of this change in EMF, you will find out that what is this delta T. Okay, so every time we need to find out what is delta T. So here your EMF, your electromotive force, is directly proportional to what? Delta T. So if you know this EMF, you will know what is your change in temperature. And what is that principle? That is why I have drawn it with two different things. One is that two different metals are meeting at two junctions and at two different temperatures. Then there will be an EMF generated between these two, and this EMF generated will be directly proportional to what? Change in temperature. That is the temperature between these two. Okay. And we already introduced that what is the thermometric property here? EMF. What is thermometric property? Thermometric property is EMF. Okay. Next. Then there is one thing opposite of this effect, that is called Peltier effect. This effect is what? That this is opposite of Seebeck effect, and then if there will be an EMF passed through to different temperatures and two metals, then there will be what? The difference in these temperatures. Then this is giving you what? This is giving you thermoelectric refrigeration. Thermoelectric refrigeration. Okay. Next thing is constant ideal gas thermometers, and one of them is constant volume. These are what? Ideal gas thermometer. So one is constant volume thermometer. So constant volume thermometer, what happens into it? See, we know this gas equation. When we will study about gas, we will study more number of laws, but for time being we know this equation, right? So can we appreciate this fact that if this volume is constant, can I write down this gas equation as that P1 V1 upon MRT1 is equal to P2 V2 upon MRT2? Okay, so if this is a constant volume thermometer, then I can term that volume is constant. Okay, and I can also say that mass and R, these things are not going to get changed. Then can I write down this equation has been reduced to what? P1 upon P2 is equal to T1 upon T2. So what is this ideal constant volume gas thermometer? See, let us say that you were having a thermometer and you filled it with some ideal gas, and if let us say that do I show you? Yes. Let us say that you have fitted one pressure gauge. let us say that there is a container into which there is some ideal gas. Okay, into which there is some ideal gas, and there is one pressure gauge which can detect the changes in pressure. Okay, so what happens is that, let us say there is some gas into it. Okay, okay, now if there is some temperature change, and if this is rigid, if this is rigid, that means that it cannot change its volume. Then pressure, volume and temperature, three things are there. If volume is fixed and temperature is getting changed, that means pressure must change itself. That means your pressure gauge will show some deflection. So can you see that if you were having temperature T1, then you have pressure P1, and now you have reached to P2, then your temperature is T2. Okay, so if your pressure gauge will help you to find out this reading P2, then can't you find out T2 using this equation? Definitely we can. So using constant volume thermometers, ideal gas, more specifically ideal gas thermometers, so this is filled with what? Ideal gas. Okay, so using constant volume thermometers with the help of ideal gas, can we see that with the change in pressure, I can find out what are the changes in temperature. So here your thermometric property for constant volume thermometers, thermometric property is thermometric property is what? Pressure. So same can be applied when your pressure is constant. So I am moving to constant pressure, constant pressure thermometers. Then my thermometric property is thermometric property is volume. How? Here what we will do is that again I am directly writing down this ideal gas equation, and I have cancelled what? MR term. So can I write down P2 V2 upon T2? And here we have already mentioned that it is constant pressure thermometer. So can I cancel out the pressures also? So this equation becomes V1 upon V2 is T1 upon T2. So if I know volume at two time instance V1 and V2, then I can know the temperatures also if I am using what? Constant pressure thermometers. More specifically, we are writing these equations for whom? Ideal gas. These are ideal gas thermometers. Okay, so can you see that if we are using ideal gas thermometers, then there is no dependency upon the material. That means that if we are using oxygen, nitrogen or any ideal gas, then there is no dependency upon the nature of the ideal gas, because here there is no specific property related to that gas. Why? Because the property terms are getting cancelled out, right? So we can we see that ideal gas thermometers are independent of material of construction. So can I write down that ideal gas thermometers are independent independent of the material of construction. In other cases, your properties like delta R, EMF, what we can see that the nature of material which you have used, based on that there can be some variations, right? But in ideal gas thermometers, there is no such dependency. Yeah. Okay. Let us now quickly move to temperature scales. Okay. So just one thing we need to remember about temperature scales and nothing much to be worried about it. Okay. So temperature scale. See, what is temperature scale? What you will do is that, let us say that there is one notation into which you have some steam point, ice point and steam point. See, temperature scales are dependent upon two temperatures, means two constants. One is defined as that particular, let us say that I am analyzing it in degree Celsius scale or Fahrenheit or any given scale, then I have two fixed things that the system will convert into ice at some given temperature. Let us say that that is T ice, and the system will start, let us say that any particular substance will start boiling at some given temperature. Okay, so these two things are fixed. Okay, the steam point and ice points are fixed. So the linear variation between these two is that, like if you are using any let us say that if this is in degree Celsius scale, and let us say that if you are trying to apply it in Fahrenheit scale, let us say that the same thing, if you are applying it in Fahrenheit scale, then it must have again steam ice temperature and steam temperature in degree Fahrenheit also. Okay, so how we correlate between these two, that if we know that there is linear variation, then we know that T ice minus of, sorry, T not ice, T, yeah, T gain any given temperature. Let us say that you are talking that what is the temperature in degree Celsius and the same temperature in degree Fahrenheit scale. Okay, so let us say that you are at T and T ice, okay, divided by, this is T steam minus T ice, this will be equal to that in the change scale. Let us say that if we are using it in degree Celsius scale, so that particular scale, this will remain constant. Let us say that we are using it in now Fahrenheit scale, so I am writing down it in TF. So TF minus T ice divided by T steam minus T ice, and this is in, if I write down, this is in Fahrenheit scale and this is in degree Celsius scale. So these two things will be correlated. Now, based on this, you can, let us say that you can develop even your temperature scale, like any temperature scale can be developed based on this fact. So we know that in ice, in degree Celsius scale, your ice point is 0 degrees Celsius and your steam point is 100 degrees Celsius in degrees centigrade. And in Fahrenheit scale, we have ice point at uh, 32 Fahrenheit, 32 degree Fahrenheit, and steam point at 212 degree Fahrenheit. So we using this convention, you can what, develop a relation between degree centigrade scale and Fahrenheit scale, and using this relation we can identify the relationship between any of the given scale. Let us say that there is an n scale, there is p scale, any scale. They will tell you that okay, its ice temperature is this one, stream is this one. Then you can find out the any given temperature in that particular scale compared to any scale. Let us say that what is the temperature in Fahrenheit scale, and let us say that given temperature is 10 degrees Celsius. Then they will ask you that same 10 degrees Celsius will saw how much in Fahrenheit scale. So using this relation, we can always find a relation between these two. Okay. Okay. So this is all about Zeroth's law of thermodynamics. Okay. Now let us understand energy and its interactions, because till now we have not talked anything about energy, because ultimately we need to find out what are the energy changes happening to that particular system. So we should know that what are the ways of energy interaction and what the energy itself constitutes within. Okay, so let us now understand what is energy. Energy, anyway, we know, and its interactions. So energy itself possesses as microscopic and macroscopic. Let us understand what are these two. See, microscopic and macroscopic. Macroscopic means your body as a whole. Let us say that there is a body, this one, and I have changed its elevation. Let us say that I have made this body reach from this point to this point. So there is some delta H, right? So this body as a whole has moved from this point to this one. So due to these, like what I do say is that let us say that this body as a whole possesses some energy. What do I mean is that let us say if this is your datum level, then this body as a whole has some distance from your datum. So it is possessing certain kind of potential energy. Yes or no? So it has some potential energy at this point. And again, if this body is transferred to some another another height, so then again your datum distance between datum and this body has changed, right? So this is H plus delta H. So again your potential energy has been changed. Let us say that initially if this is mgh, now your potential energy is mg into H plus delta H, right? So now this is body possessing itself as a whole. We are not talking about any molecular level, right? So that is why name it macroscopic. Let us say that if this body was having a velocity of 10 meter per second at this point, and when you are changing the elevation, it is also changing its velocity by some mean. Let us say that this velocity is 20 meter per second. Then this body as a whole has some kinetic energy also with it, right? With it. So this kinetic energy is half mv square. Let us say that this at this point, if this is 1 and this is 2, then this is half v1 mv1 square, and it has reached to half m v2 square. So can I see there is some difference in this energy again? So what are the macroscopic energy? These are those energies which body possesses itself as a whole. So it can be macroscopic energies, can be what? It can be kinetic energy and it can be potential energy. Got the idea what is body as a whole? See, what do I mean by body as a whole? Like this is not dependent upon the molecules. This is not dependent. Like see, if you are at H, then your macroscopic property, let us say that energy, macroscopic energy, let us say potential energy. This is not dependent upon that what is the temperature of this body. Let us say that if this is at 10 degrees Celsius or it is at 100 degrees Celsius or whatever temperature it is assuming, it is at molecular level, right? But the body as a whole has certain elevation, so your macroscopic property is dependent upon that elevation only. It never minds that what are the mm, what is happening with the molecules or what is the temperature of that particular body at any instant. Got the idea? But what is meant by microscopic? Let us say that you are having certain temperature with you, right? When I am changing your temperature, let us say that at the same elevation, see this is H, and at the same elevation at another instant you are having, let us say initially this was at 10 degrees Celsius, but now if you have reached to 100 degrees Celsius, now your macroscopic energy is constant. Why? Because this H value from the datum is again same only, but your energy due to temperature has got changed. That means which energy has got changed? Microscopic energy. The body as a whole has not changed, but its molecular energy has got changed. So that means this microscopic energy must constitute things on molecular level. So we have microscopic energy. It is also named as internal energy. Internal energy, and it constitutes which parts? First is sensible, second one is latent, third is chemical, and the fourth one is nuclear. Okay, let us understand this quickly. See, sensible means what? That if you were having at 10 degrees Celsius, now you have reached to 100 degrees Celsius. That means you must have stored some energy in this duration, right? Reaching from 100 to 10, from 10 degrees Celsius to 100. So that part is gone into which you can directly sense. That is sensible energy. Then what is latent? Let us say that from 100 degrees Celsius, if you provide more heat to it, the substance is not changing its temperature, but it has started changing its phase. That means now your bonds have started getting broke, right? Like let us say that if this is a high H2O molecule, then what? The bond between two H2O molecules have started getting broken. Then I can say that this is hidden into what? Latent energy, at the molecules have started getting broken. So latent energy is that part that now your substance has started changing its phase. It is not sensing any temperature change, but it has starting its what? Its phase change. And the third one is chemical. Now if the bonds between H2O is broken, then that part is constituted in which one? Chemical. And if the atoms are again broken, then that is nothing but nuclear. So our concern is only these two parts. We are not worried about that what happens with the chemical and nuclear energy. We are only worried about sensible and latent, and more precisely sensible only most of the time, but latent is also important. So the microscopic energy constitutes of sensible energy, latent energy, chemical and nuclear, and your macroscopic energy constitutes what? It constitutes kinetic energy as well as potential energy. Okay, so we'll finish today here only, and then later on we will appreciate the work interaction, heat interaction, and other things. Yeah. So we'll stop here and we'll meet in the next class.